So let's go ahead and jump back in. So you can see here on the screen, I've got some properties of limits pulled up. We're going to talk about this. So I talked yesterday about some, like the definition of limits. That's kind of where we were at. It was up here. I talked about the textbook definition and kind of how we can visualize what limits are. And then we started talking about some basic properties of limits. And we ended up talking about, scalar multiplication, addition, and then multiplication of scalar valued functions and how the limit affects all of those. But the question is, how do I, if I don't have a scalar valued function, this last one here, as you can see, f of x is not a scalar valued function. It's an the outputs are m dimensional. So the limit of this f of x should have m coordinates, right? Because f of x, right, the output of f. So if I plug in a specific x, I get f of x. That's going to have m dimensions, right? And so the limit of that is going to be a point in Rm. So that's what this is here. This last this last property here is saying, okay, how do these individual coordinates relate to this limit here? And the way that they relate is that this limit converges to this point with these coordinates if and only if the limit as xi goes to x naught of fi of x is equal to bi. Okay. And one thing I have to tell you is what this fi is. So where I would usually write something like where f of x is equal to f1 of x, fm of x. So basically what we're doing, this looks kind of complicated and like there's like a lot of notation going on. But what we're doing is we're taking the limit of some vector valued function. So the function has values which are in m dimensional space. In other words, they have m outputs. You can just think of that function as being broken up into m scalar valued functions, right? So that's what this notation means here. We've taken f, right, which is an m dimensional. It's vector values and output. It has m outputs, and we said instead of thinking of it as having m, is this thing having m outputs? We could think of it as m separate scalar valued functions. So each of these is scalar valued. Let me write that in a different color. Let's do that. So this here is scalar valued. Each of these independently. And what we can do, what this is basically saying is if you break your function, if you have this vector valued function, you want to take its limit. That sounds hard. So the way we do it is we break it up into a bunch of scalar valued functions and we take their limits independently. And if we do that, then we can put that all together back into the coordinates and we get the limit there. Does that make sense? We'll see some examples here in just a second. Okay. So let's try to go through some examples. Let's look at this example here. Okay. So let's start with this example here, right? So here we have it's a scalar valued function, x plus yx, or sorry, x plus yz, and it's in 3 variables, x, y, z. Okay, and the question is, what happens to this as x goes to 1, y goes to 0, and z goes to 1? Okay, so if you remember from your single variable calculus class, when you take a limit, what's the first thing you should usually try? It's like the one thing that you hope just works off the bat. Anyone remember? If you're computing the limit of something, even if it's just x goes to some number. Yeah, direct substitution, plugging it in, just see what happens if you just plug in these numbers. Is that going to be a problem, right? In practice, that we can talk about all of this like theoretical definitions and stuff, but at the end of the day, when you're actually computing a limit, your first try is to just plug it in, see what happens. So we can just plug in all of these numbers and we get that this is equal to 1 plus 0 times 1, which is just 1. Okay, so this one's not bad at all, right? It's just same as the limits we were taking before back in single variable calculus, except now there's 3 variables. And so you have to keep track of all of them. Okay. We'll see later that it's usually the limits that don't exist that are going to give us, that are going to be a problem. Okay, the limits like this that you just plug in and it works out are going to be the simplest ones we do. Okay. So now if we look at number 2, right? If we look at number 2 here, what if we plug in, if we try plugging in, we get sine of 0 over 0, which is just 0 over 0, right? That's not allowed. That's not okay. 0 over 0 is not okay. Now, if we were in single variable calculus class and we saw something get 0 over 0, what would we use to get past that hurdle? Okay. That's a 0 over 0 is called indeterminate form. Yeah, so we'd use a L'Hopital's rule. But in this case, there's 2 variables hanging around, right? There's x squared, there's x and y. Okay, and we're going to learn later today about how to handle differentiation when there's multiple variables, but that's not going to help us in this particular situation. So the interesting thing we're going to do here is we're going to make a substitution, because we realize that even though we're taking both x and y to 0, in this equation they're somehow related, and so we can actually introduce a new variable. So introduce, in this case, it's a variable we've seen before, because I see x squared plus y squared. I can just call that r. And I know, maybe I shouldn't call it r. Maybe I'll call it t, is equal to x squared plus y squared. Now you could view this a couple of ways. You can say, instead of calling it t, you could say that r squared is equal to x squared plus y squared. And you could say I'm converting to polar coordinates, not polar coordinates. Oops. In this case, that would be cylindrical coordinates. Oh, it's xy. So yeah, it's polar coordinates. So you could say I'm going to convert to polar coordinates here. That's an option. But in some equations, as you'll see later, it's not always obvious how to make that substitution. Later, or maybe on the homework. I think on the homework, there's some examples of problems that the substitution you're making is not going to be necessarily like something nice like polar coordinates or spherical coordinates. It's just going to be an arbitrary thing. But if you notice like the same chunk of stuff that depends on both variables in like multiple places, that's a good sign that you're going to want to do some kind of substitution. So here we do this. Now suddenly taking xy to 0, 0 is the same as taking t to 0. Both of those things are equivalent, right? And so this limit becomes the limit as t goes to 0 of sine of t over t. If you remember our warm up from yesterday, we computed this limit. What was this limit equal to? It's 1, yeah. So this one you can remember using L'Hopital's rule, right? Because it's 0 over 0 if I plug in. So then you take the derivative cosine over 1, plug in 0, you get 1. Okay. Let's recap what we did there. We had 2 variables. It was hard to keep track of them. We didn't know how to proceed with 2 variables. So we realized that the 2 variables we could just turn into 1 variable, which feels kind of like cheating, but it works out, right? Because the important thing is that as xy goes to 0, 0, x squared y plus y squared goes to 0. This is the important thing. This is the reason we're allowed to make this substitution, because that means that we can replace this here with, well, this is just t goes to 0. So that means that this and this are directly interchangeable. Yeah, so after the substitution, I basically use L'Hopital's here. So if you go back to your Calc 1 notes, technically when you learn about this limit, it doesn't use L'Hopital's, it uses the squeeze theorem. And the reason for that is that you need this limit in order to compute the derivative of sine technically. And so for technical reasons, you're not supposed to use L'Hopital's rule, but I use L'Hopital's rule as, on this just as like because it does a way to confirm that I remember it. I always remember it's either 0 or 1. And so you could use L'Hopital's rule to remember, oh, it's 1. Mm-hmm. Okay, cool. Any other questions? Okay. One last little exercise for this part of the notes. Okay. So let's prove that this limit doesn't exist. Now this is going to be a little trickier, right? Proving that the limit does not exist actually ends up being a little trickier in this case. So remember in Calc 1, how we would prove that limits didn't exist. There was a few ways. Depending on how you were taught, sometimes people would say, well, if it goes to infinity, then it doesn't exist, right? That's one way to think about it. Though some people like to say that, well, if it goes to infinity, we say it exists, but it's infinity. And so they kind of distinguish between that. But let's say if we want to prove it honestly, it doesn't exist and it's not infinite. Okay. Well, the way we would do that, does anyone remember how we would do that if we had this single variable function back in calculus, it's Calc 1? We said, I want to prove that the limit does not exist. Anyone remember how we would do that? So if the limit exists, that means that the limit from the left and the right are the same. So if you want to prove the limit doesn't exist, so that leads to n over 0. That's an option, proving that there's like a division by 0, though that's kind of more in the infinity part of things. The limit not existing, the way we usually do that is we do the left and the right, right? So you do the limit from the left, see what happens, do the limit from the right, see what happens. If those numbers are different, then the limit does not exist, okay? Because the limit from the left and the right are different. In this case, we don't have a left and right because we're talking about the origin in R2, right? So there's no left and right here, okay? Or there is left and right, but there's also up and down and side to side, right? So what we're going to do here is we're going to make additional assumptions. And what that's doing is that's affecting the direction from which we approach the origin here. So I'm going to draw the coordinate plane here. And it's important to remember that this isn't the graph of this function. This is the domain of the function. Okay, so this is your xy plane. And you want to approach the origin, of course, right? That's where we're ultimately headed. But we can approach from a lot of different ways. Now, before, for example, if I go back a problem here to this t equals x squared y squared, what that's doing is it's drawing a circle and it's having that circle shrink down to 0, okay? That circle is shrinking down to 0. That's what this problem was, letting t equal x squared y squared. And now this, what we're going to do is since we want to prove it doesn't exist, we don't want to find something that we can just have everything go to 0, we're going to go to 0 from a couple of different angles. So for example, what if I want to go to 0 from the x-axis here? If I want to just approach it like this and like this. What if this is how I want to approach the origin, right? Well, let's think of the equation for the x-axis. The equation for the x-axis is y equals 0, right? So what we could do is we could try to make that substitution over here. Well, the problem is that at y equals 0, this is not defined, right? So at y equals 0, this is this limit of x plus x squared, or just x squared over 0, does not exist, right? Okay. Well, if it doesn't exist from one direction, maybe you could say that this that means that this whole limit doesn't exist, right? But we can also approach from other angles. So let's see what happens if we approached from a different angle. Okay, so I'm gonna use a different color. What if we had instead approached from the y-axis, or yeah, from the y-axis? Now this is x equals 0. So over here we have at x equals 0, we have this limit. So all I'm doing is I'm replacing, so here I replace this limit with all of the y's equal to 0. So then the limit part, the y part of the limit goes away, and it just became x goes to 0. Now if I plug in x equals 0, the opposite happens. This is the limit as y goes to 0 of 0 over y squared, right? 0 y plus 0 is 0. And then this simplifies to just 0, right? Because then this is just the limit of 0. So that's 0. Okay, so we got different things. That's good. Okay, but just for practice, like, so let me, I guess, make a note of that. So these two are different. So the limit does not exist. Okay. But let's pretend we wanted to be really sure. Like maybe we saw this DNE thing and said, well, technically that's not part of the domain of this function. Maybe let's just ignore this. What if it doesn't exist when y is 0 and it's 0 everywhere else? Then the limit kind of exists. But also maybe you didn't do this one first, right? Maybe you started with this and you want to approach from another one. Do we have to write a sentence on the quiz? It's always helpful to write full sentences. It makes it easier to kind of see. But overall, I would, if you show your work and then just write something like equals d does not exist or does not exist, that would be fine. Let's do one last. So let's say now we want to approach, instead of along these axes, let's approach like at an angle here. So here in green, we want to approach from this angle. We need a nice equation to go with this too. What's the equation for this line here that's coming in at an angle? Anyone? So goes through the origin. The slope is 1. It's just y equals x, right? Along this line, y is equal to x. So what we can do is in our equation, set all of the y's and x to the same thing. So you can think of this as saying, let all of your y's equal x. So then the y goes away and we get this limit as x goes to 0 of x squared plus x squared over x squared, right? All of the y's became x's, so you get x times x, which is just x squared, plus x squared, divided by this y becomes an x, so it becomes x squared. So then this is the limit as x goes to 0 of 2x squared over x squared, which is 2, right? The x squareds cancel and you just get a 2. So if you weren't sure before, right, we got a 0 and we got a 2. That's enough to say, okay, the limit does not exist. Okay. So this is going to come in a couple of different forms. There's going to be sometimes the question is going to be presented like this, like prove that this limit doesn't exist, or they sometimes like to avoid using the word prove because that scares people. So maybe it says like show or explain why the following limit does not exist. Okay. And so you already know that it doesn't exist. And so your strategy is just, okay, let's come at it from a couple of different angles and show that it doesn't exist. Now, sometimes it's not going to be completely clear what angle to come at it from, or what what substitution to make here. Because sometimes you're going to like your first two choices are going to give you the same limit, and you're going to be like, oh, maybe this limit does exist. Okay. And so you're going to have to get kind of clever with your substitutions. There's some on the homework where it's not as straightforward. It's just like x equals 0 and y equals x, right? Maybe one of them is like this, but then the other one is kind of tricky to see exactly how to make that limit work. Okay. But sometimes it's just going to be like, hey, here's a limit. Determine if it exists, and if it exists, then compute it. Right? It's going to be like over here, I told you to compute these because they had limits and they existed. This one I told you, if limit doesn't exist, show that it doesn't exist. But sometimes it's going to be like, hey, here's this limit. You figure it out, right? Like that's going to be kind of how it's presented. And so in a situation like that, I might try, a couple of different angles, or I might try something like seeing if it exists, something like this. Of course, always try plugging in the number, see if that works out. If that works out, then you're golden. But yeah, and then maybe try some single variable techniques with see if you can get it down to one variable in a way that something like this happens, right? That you can kind of make sure like, okay, we're getting it down to one variable, but we're not losing any information. We still have all of the information here. Oh, oops. Okay, cool. Any questions on these sort of limit problems? There's more on the homework, and I think they're good practice. So for the sake of time, I can't do like a million of these. If not, I would totally be happy to. But I would definitely suggest, once you're done with this week's quiz, then start working on that homework. And then if you have questions, come to my office hours tomorrow morning. Last week, one person showed up to my office hours in the morning, and I think they got a lot out of it. And so if you're having questions on the homework, then you can come. And a lot of it is going to be like little clarifying points. Like you're just wondering what they mean when they say this, and it's going to be like, I can just clarify it real quick. Okay. The next thing we're going to talk about is continuous functions. So we talked about limits, and if you remember back to your single variable calculus days, after we talked about limits, we talked about continuous functions. But now we're going to talk about continuous functions in several variables and potentially vector or scalar value. So how do we know if a function is continuous? Well, we first talk about being continuous at a specific point. Being continuous at a specific point is what that means is that, remember, x naught is a point in n-dimensional space, is we take the limit, I think that's okay. We take the limit as x approaches that point of the function, and that should be the same as just plugging in into the function. Okay. So we said earlier that one of our techniques for computing a limit is that you can just plug in try to plug in. Now, what this is telling us is only certain functions that only work for certain types of functions, and we call those continuous functions. Okay, and so you have that this is the definition of a continuous function. You have f of x equals x sub f of x, the limit as x goes to x sub 0 is equal to f of x sub 0. Okay. So what that means is that, right, it doesn't do something weird at the point, right? Because what the limit is saying is, judging based on everything around x sub 0, what is f of x doing? Well, f of x looks like it's going to this point. And on the other hand, what does f of x actually do at that point? And those might be different. If they're different, then it's not a continuous function. If they're the same, then it is a continuous function. Okay. Okay. And so yeah, just like there's two definitions here. This one is technically it's continuous at a specific point versus it's continuous all around. Okay. Okay. Sorry about that. I just wanted to look ahead a little bit to see if I needed to include one other definition on this slide. So sometimes we say that a function has a point of discontinuity. So a point of discontinuity is a point in the domain such that the limit as x goes to x naught, f of x equals f of x sub 0, if these are not equal. Okay. So as you can see, if a function is continuous at a certain point, if this limit equals this, but if they're not equal, then we call that point a point of discontinuity. And one of the common ways we're going to see this is if the function is just not defined at that point. For example, dividing by 0 is probably one of the most common discontinuities we're going to see. And I'll talk about that in a couple of slides. All right. Cool. Okay. Give you all a second to catch up on writing that. But so we have these notions of continuous functions, but they're defined based on limits. And so we're going to look at some properties of continuous functions, which are going to be very similar to the properties of limits that we worked on at the end of lecture yesterday and we started with today. Okay, so let me jump to those. Okay, again, I post the notes after, so if you didn't quite make it, if you weren't able, I understand, like I have some stuff pre-written, so it might take you a while to write everything down. So you can always catch up on it later. Oh, sorry. Good question. Good grammar question. No, this if here, or yeah, we're talking about this if and this if. This if should be an is continuous at a point. Thank you. This one's an it, so also I don't know if that one was, if you were thinking of this though. I'm trying to see if I missed that anywhere else too. No. Okay, cool. Yeah, so just this part here. So this here, right? So the important thing is that the continuous at a point means it is defined using this limit. And just we can say that a function as a whole is continuous without saying at a point if you can pick any point in the domain and it's continuous at that point. Okay, so nothing weird. Like basically you can think that like there's a way you can check every point and you can say, okay, it's continuous there, nothing weird happens, nothing weird happens, nothing weird happens at every point in the domain. Cool. Cool. We'll see some examples here in just a second. Okay. But first, let's talk about some of the properties of continuous functions. Again, these are going to be very similar to the properties of limits. So, for example, if you have a continuous function, then some scalar multiple of that continuous function is also going to be continuous. And these are going to, like I said, these are going to look similar to the properties of limits because they're based on the properties of limits. Remember, being continuous is defined using limits, right? And so it makes sense that all of these things, all of these properties are going to be very similar. So if you have two continuous functions, if you remember what we did with two limits which existed and we added them together, right? So here, if we add them together, they're still going to be continuous. So all of this is doing is it's saying, hey, if you know just a handful of continuous functions, or if you figure out that a certain function is continuous, you don't have to prove that other functions are continuous if you can just write them as like the sum of two functions you already know are continuous, or a scalar multiple of functions that you know are continuous. Or in this case, right, m equals 1, right? In this case, we have m equals 1 over here. You can take the product of continuous functions, of scalar valued continuous functions in this case. You can only take products if they're scalar valued, right? So you have that. I dropped an is, but it's okay. Okay, so you take the product of two functions, you can take the scalar multiple of two functions, you can take the sum of two functions. So one thing you can build from all of these is if you know that the function f of x equals x is continuous, which it is, then you can prove that any polynomial is continuous, right? Because a polynomial is just like, well, x squared is just x times x. X squared, 2x squared is just c times x. And then if you have like 2x squared plus 3x, that's just, that's just some combination of all of these using just the x, right? And if you tack on a y in there too, it's still just combinations of all of these. Okay, cool. Now this one is new. This one didn't come from limits because we didn't really have it before. But here we can see that f goes from n to m, and an h goes from k to n, right? So if we can plug in something into h, gives us something in Rn, and then we can plug that into n or to f and see what happens. And it turns out that that's still continuous. So the composition of functions is continuous. Technically, that should be a y. So they're different variables here because they live in different domains, right? That's the reason I use different letters there. Okay. So the composition of continuous functions is continuous. So, for example, if I know that the trig functions are all continuous, which we do from calculus class, then I can take some polynomial and plug it into a trig function, and that is still a continuous function overall, right? Cool. Now this last part, this is f is continuous if and only if. This is going to relate to that last property of limits that we talked about at the beginning of lecture today, that we started with today. Okay, so what that is we say f of x is continuous if and only if fi are continuous for all I And again, just as a reminder, what is this f sub I? Well, we're just thinking, we're breaking up f of x, which is a vector valued function. We're breaking it up into its scalar valued parts. This is going to be a common trick that we see in this class, is you take a vector valued function and you just give a name to all of the vector value, or the scalar valued parts, the coordinates, right? This is going to be common, especially when you get to the real like calculus stuff and differential, like derivatives and stuff. And so we're going to want to, if we have a vector valued function, you could break it up into its scalar valued parts. Okay. Just in general, dealing with scalar valued functions tends to be easier. And so that's why we try to break up, anytime we have a vector valued function, we want to grasp it. So we try to break it up into its vector valued, scalar valued parts. And using that, we can prove that certain, like if a function is vector valued and you're like, oh, that's, how do I prove something that's vector valued is continuous? Well, you just break it up into the scalar valued parts and you justify each of the scalar valued parts separately. Okay, each coordinate basically. Okay. Okay, so like I mentioned, I want to get into some examples. But like I mentioned when I was talking about these properties are a way for us to like prove or show that certain functions are continuous without necessarily like using that, like using the, having to compute a limit or doing something crazy like that. We can just kind of build off of some basic building blocks and just combine them either by doing scalar multiples or adding continuous functions or multiplying scalar valued functions or composing functions or just showing that the parts are scalar valued or the scalar valued components are continuous, I should say. Okay, so let's go ahead and go to this. So I want this to be kind of like a list of some notable continuous functions. Most of these are going to be single variable functions, but as we saw over here, we can always, not single variable, they're going to be scalar valued functions, I should say. But we can always break up a multi-valued function into scalar valued parts. And if the scalar valued parts are continuous, then we're good. So we can use these to build even vector valued functions, if even with just scalar valued functions that we have. So some of them we're already going to know. So polynomials. And the notable thing about this is that can include polynomials in several variables. So for example, we might think of a polynomial as like x squared plus 2x plus 1, but that can include you can have polynomials that are like x squared plus 2xy plus y or something like that. So you can have multiple variables in the same polynomial. Of course, we have our trig functions, which we love from calc. We can have exponential functions. So we have like e to the x or 2 to the y, stuff like that. We can also have logarithms. Right, so with any base, you can have that. Am I missing anything? Yeah, so like roots of functions, roots. So like the square root, the cubed root, I should say x, the cubed root of x, whatever. Though with the even ones, you are going to have to, it's like only continuous if you restrict to the positive numbers, right? Can't plug in negative numbers. Okay. Okay. Now, notable discontinuous functions. This comes up in different ways, but you can have f of x equals 1 over x. It's going to be discontinuous. So basically just don't divide by 0 is going to be like one of the big things. Right? And then along with this same lines, like 1 over x minus 1 or something. This was like the main way we built discontinuous functions before. But also like some piecewise functions, right? So like if you have one function coming in from the left, one other function coming in from the right, and they don't meet up, then that's a discontinuity. Right, so I'll draw a picture of that. Okay. Again, all of these are in are scalar valued, but we can just check the components, and if any of the components are made up of any of these things, then you have a continuous function. Or if all of the components are made up of these things, you have a continuous function. Okay. Cool. So these should all look familiar, but this is going to kind of be our toolbox. I'm trying to think if I missed any common continuous functions. Most of the functions that we learned, like anything that had a nice name to it that we learned about back in pre-calc and calc, are gonna be continuous. Okay, cool. So let's see some actual examples. Here's an example here. So we have this function, which is defined piecewise. So away from 0, 0. So basically what they're saying is, so I'll over explain this problem just a little bit because it's our first one. Basically, away from uh, 0, 0, sine of x squared plus y squared over x squared plus y squared is a composition of continuous functions, right? It's the trig function, and then it's a composition of continuous functions. It's a trig function, and then it has a polynomial plugged in, and then there's a polynomial in the denominator. Again, I guess maybe I could have included that. Like 1 over x away from 0 is continuous, but here we have, if we're away from 0, so this dividing by this number, that's totally continuous. So then, we taking sine of this and dividing by all of this, it's still continuous. So it's continuous. Again, still away from the origin, this function is, I was going to say very obviously continuous, but I guess it's only obvious if you've taken all of these kind of building blocks for granted, right? But basically, it's built out of continuous functions, and so it's very clearly continuous. The only problem might occur at 0, because the question is, well, this function is not defined at 0. So what we have to do is we have to cook up a value of c so that this function is, so that when we make it a piecewise function, so that we actually give it its own definition at 0, 0, away from this formula, we can get something that's continuous. So if we want it to be continuous at the point 0, 0, well, what does that mean? That means that the limit as xy goes to 0, 0 of f of xy is equal to f of 0, 0. But on the right-hand side, we have f of 0, 0. If we look at the way the function is defined over here, it's a piecewise function. When xy equals 0, 0, then we just get c. But when we're taking this limit, as x goes to 0, 0, we're not at 0, 0. So we're going to use this formula up here. So we have the limit as xy goes to 0, 0 of sine of x squared plus y squared over x squared plus y squared. Okay. And now we've reduced it to this limit here. What is this limit that this limit is a limit we took earlier, right? Remember, we let t equal x squared plus y squared, plugged in t. This is the limit as t goes to 0 of sine t over t, which we took earlier, and that limit is just 1. So c equals 1. So that there is our final answer. Okay. So the moral of the story, if you're asked to prove something is continuous and there's nothing being divided, you just have to show that it's built. You just have to see if it's built out of sort of these functions here, right? Sort of the basic sort of building block, out of the basic sort of building blocks of continuous functions. Okay. And the only time you're gonna, well, the only time you're gonna see kind of potential discontinuities is dividing by 0 or some weird piecewise stuff. Okay. For the most part, it's going to be this dividing by 0 thing, but there are some discontinuities which we can fix here. So, for example, this function is not continuous because it's not continuous at the origin. This function here, just the sine of x squared plus y squared over x squared plus y squared. But if we define this new function, which is mostly the same, except at 0 at the origin, we give it some other value, in this case, c equals 1, then now this function f of x, y is continuous. Okay. Does that make sense? Again, there are more examples in the homework for you to like go through and practice those. And if you have questions, feel free to stop by office hours, post them on Canvas. Okay, cool. Okay. So let's move on to we're going to move on to the next section, which is where the more exciting stuff starts to happen. Here we had continuity. Next, we're going to deal with differentiation, which is for a calculus class is like the meat and potatoes. Okay. Let's move on. Open this. And again, if you have questions on that continuity stuff, if I know I didn't do a whole lot of examples. I wish I had time to do like a whole bunch of examples, but if you have questions on any of that, you can ask them in office hours. You can ask them on Canvas, and we can try to get those answered. Okay, cool. So today we're going to talk about, for the rest of the class, we're going to talk about differentiation. We'll get through it today. We'll finish up on tomorrow morning, and yeah. Okay. Let's see. So I kind of liked what I did with the continuity section, where I kind of showed you the textbook definition and kind of just riffed off of that. So I'm going to do it again here with differentiation. Particularly, we're talking about what we call partial derivatives here. So this is like a fancy definition that it's good that we keep this in the notes. Again, I referenced the page here, so you don't have to write down this whole paragraph. You can just write down the page number and then either write it down later, or maybe later take a screenshot. If you're doing your notes digitally, you can put that in your notes. But basically, you have we're talking specifically about real valued functions, or not real valued, scalar valued functions, because you're noticing here. Let me make sure I have a good color. Here we have a scalar value. Here we have the range is R1, right? The outputs are in R1, which is just scalars, right? Just numbers, not vectors. So real scalar valued function. And we're defining these things called the partial derivatives. And this is the notation we use for the partial derivative right here, okay? So the difference between a derivative, right, which we had df dx or something like that, is these, we still use df dx, but that's how you pronounce it, but the symbol is this like squiggly d, or a reflected 6, like a backwards 6, if you will. And so this is, you still pronounce it as d. You'd still pronounce it the same way, df dx. Or you could say partial f with respect to x, j. And now notice we take it with respect to one of the specific coordinates because we're plugging in vectors, right? The inputs are still vectors or n-dimensional objects. And so we do that, but we're taking it in the j direction. So this definition here, this limit here, should look familiar when we took single variable calculus, right? If you remember, in single variables, the derivative was f of x plus h minus f of x over h. And we took the limit as h goes to 0. Here, we're only adding the h in this particular coordinate. Okay. So we're taking the derivative in one specific coordinate. So basically, let me summarize everything over here on the side. df dxj is basically just ignore the other coordinates. In other words, treat them like constants. And differentiate with respect to xj. Okay. So this is what a partial derivative is. You ignore the other coordinates. In other words, you treat them like constants. You treat them as if they were just numbers. And then you take the derivative with respect to one specific variable. Okay. Cool. Okay. Yeah, so this is for scalar valued functions. We're going to learn later how to deal with vector valued functions, but basically it's just break it up into its scalar valued parts, and then you can take scalar valued, you can take partial derivatives of the scalar valued parts. But yeah, let's see some examples of this. I think we jump right into some examples because I think with certain definitions like this, like the derivative, it's best to just jump right in, right? I mean, I think you remember that probably from calc class. I don't know, when you first start learning about derivatives in calc, you spend like a week talking about just this definition and how to use this definition. And then we teach you like, okay, well, there's all these tricks for computing derivatives that make it just way easier. And so you can just use that. And so we're going to just jump into doing some examples. From this point forward, I'm going to assume, you know your power rule, your product rule, your chain rule, all of that. And we're going to be able to use those kind of freely as we see fit. Okay. But there's going to be more than one variable hanging around. So, okay. Cool. Let's see. So we're going to compute the partial with respect to x, the partial with respect to y, and the partial with respect to z for the following functions, each of these functions. Okay. So let's start with number 1 here. df dz, or dx, I should go in order. Df dx is we're going to take this derivative with respect to x. So what we do is we treat this z and this y as if they were numbers. Think this is like, pretend this is like a 3 and this is like a 4, and just treat them like numbers. Okay. So remember, when you take the derivative and there's a constant in the front, you can just pull that constant out, right? Or there's a constant being multiplied, you can just pull that constant out of the derivative, and then the derivative of y squared with respect to x is just a constant, right? Y doesn't change. The way you could think about this is we're treating them like constants, but they're not constant. But what you could think of is we're just moving in the x direction. So y is not changing. Okay, so y does not change with respect to x. And remember, derivatives calculate a rate of change. And since y and z are not changing with respect to x, then their derivatives are treated as if you were taking the derivative of a constant. Okay, so we get a 2x here and 0 here because we take the derivative of this with respect to x, and then a z being multiplied still, right? Remember, scalars being multiplied get pulled out of the derivative. Okay, and that there is our derivative, right? Let's move on to Dfdy. This is going to be similar, right? So the derivative of all of this, remember, you can pull the z out. You can also factor or distribute the z through here, and maybe that'll make it easier for you. So this is like dd dy of x squared z plus y squared z. Now, again, as we're taking the derivative with respect to y, this first term, as y changes, this doesn't change. So the rate of change is 0. So this derivative is 0. And so we get the derivative with respect to y of y squared z. Y squared z. So the derivative with respect to y of y squared z, well, we do the power rule to get 2y, and the z doesn't move, right? So we get 2y z. Okay. Now, these two were very similar, right? We got 2xz, 2yz, because x squared and y squared here are interchangeable, but z is serving a different purpose, right? It looks different in that equation. So the derivative is going to be a little different. What do we think the derivative here is going to be? Remember, as z changes, x and y don't change. So we're treating them as if they were constants with respect to z. Okay. So this whole thing, this x squared plus y squared, is just a number when we're looking at z. Right. So someone's got it in the chat already, but we're treating this as if it was the coefficient to z. So if we were taking the derivative of some number times z with respect to z, we just get that number, right? The z, we just get the coefficient of z. And so in this case, it's no different. We just get that x squared plus y squared. Okay, cool. So I think these are not super hard to see, or not super hard when someone explains them to you. It's just sometimes looking at the equation, because it like this looks so different from like what's the derivative of 5z? Well, it's just 5, right? This looks so different from that at first you might not look at this and think, oh, what's the derivative of x squared plus y squared z with respect to z? Oh, well, it's just x squared plus y squared, right? That it takes some while to adjust your brain into thinking this way. Okay, we're going to focus on this specific variable and treat the other ones as if they weren't, they're unchanged, right? They're constants. Yeah. So some people are really particular. They want to ensure that you know that they're not constants, right? They are still variables. It's just that when you're focusing on one variable, the other variables aren't changing as that one variable changes. So for that, for all intents and purposes, their rates of change are as if they were constants. Okay. Okay. Now next problem, df dx. Well, I take the derivative of two things being added together. This one has an x, this one doesn't. So it's just the derivative of the ln of x part, right? What's the derivative of ln of x? Anyone remember? The derivative of ln of x, the natural log of x. Yeah, someone's got it. 1 over x. Cool. So 1 over x. And then again, the derivative, right, as x changes, y and z don't change, and so their rate of change is 0. So df dy. Well, now the natural log goes away because this doesn't depend on y at all. And this is, you can think of z as a coefficient on y, and so z, you just get z, and then df dz is the reverse, or that should be a z. Again, the ln of x goes away because it's unchanged. It doesn't change with respect to z, and so its rate of change is 0. Now over here, we could treat y like a coefficient, and we get y right there. Okay. 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 One last problem here for this part of the notes. Okay, so let's take df dx. I'm gonna actually move down a little bit and let's start with df dy and df dz, because df dx is gonna be a little different. So let's start with df dy. So df dy, right, we have a bunch of stuff being multiplied, but with respect to y, there's only a y and then a bunch of stuff being multiplied to it. So for y, you can just treat everything else like the coefficient on y. And so the derivative is just x sine of x z, right? And similarly for z, you get x sine of x y, right? Again, we're just like treat everything, nothing change. When you have focusing on one variable, the other stuff is unchanged. Okay. So now with respect to x, things get a little trickier. So what I'm going to do here is I'm going to say, okay, well, the y and z are unchanged as x changes. So I could treat them as constants and I can move them outside of my derivative. So this is y times z times the partial with respect to x of x sine of x. Okay. But now, how do we take this derivative? Right, we have the product of two functions of x. How do we take the derivative of that? So we have x times sine of x, which is a product, right? So we can use the product rule, right? So we use the product rule here, and we get sine of x times the derivative of x, which is just 1, plus x times the derivative of sine of x, which is x cosine of x. And there you go. That's the derivative there. Cool. Okay, so this one was weirder. So an important thing to note is that you might be thinking, okay, well, this is a product. This is just a product. Why did we only have to use the product rule for one? It's because on the variables y and z, there's only one of those hanging around. You're not taking a product of two functions of y or a product of two functions of z. But for x, you are taking a product of two functions of x and sine of x. Okay. Cool. Any questions on any of these examples I've done here? So I think going back to that like initial discussion board I announced, where I asked kind of people like what math classes they've taken. Some people have said they've taken math 46, which is a differential equations class. So if you've taken that class, maybe you've seen partial derivatives before, but we're definitely going to go more in depth in this class than you did in that class. Okay, so some of you are maybe you're starting to see, if you know the prereq chart, you know that after I think 9b, everything kind of branches off, and you have a lot of different options, and there's a little bit of overlap in the material for all of those. So for example, I've now mentioned 2 other classes at this point. Back in the last chapter, I mentioned linear algebra class, which is math 31, and now I'm mentioning math 46, which is differential equations, and because they have a little bit of overlap, and so that's kind of why I wanted to. That's why it kind of branches off. There's a little bit of overlap in all of them, but they don't really necessarily depend on each other. So like you don't need this class to do differential equations, and you don't need to take a full linear algebra class to take this class. But it is nice to kind of see how they're all connected. Okay. Cool. But the partial derivatives, there's nothing crazy about them. Just treat that just focus in on that one variable, treat everything else as if it were a constant. And then just kind of take the derivative the old-fashioned way. Okay, you have all your tricks from calc, power rule, product rule, chain rule, all that jazz. Okay, the hardest part is going to be looking at an equation and trying to figure out, okay, what am I taking the derivative with respect to, and is this a product rule? Is it not, or whatever? Okay, so let's see. How am I doing on time? So here the next thing we're going to talk about is the tangent plane. I don't know how far I'm going to get with this. This will probably be the last slide. I don't know if I'll get through this slide today completely through, but we want to talk about tangent planes. So if you remember in single variable calculus, I keep using single variable calculus as like an analogy for like the trajectory of this course, right? In single variable calculus, you learn about derivatives, and you learned about derivatives as the slope of the tangent line, right? You can think of it that way. The derivative is the slope of the tangent line. And that's a very important way to think about derivatives. You have like your graph of your curve, and then you have a point on that graph, and you take that tangent line, the slope of that line is exactly the derivative. Okay? Here you're going to get something similar, except that we have multiple derivatives, and we're trying to get a tangent plane. Okay? And it turns out that the definition here that we're looking for, that the equation for the plane tangent to the graph of this function at a specific input is given by z equals f of x naught y naught plus df d x time evaluated at maybe I should put at x naught y naught times x naught x minus x naught plus df dx or dy, and then you plug in x naught y naught times y minus y naught. Right? So this looks very similar to the equation for a tangent plane, right? If I say this is or the equation to a plane, I should say. It is the equation for a tangent plane, but the general equation for a plane, right? You had some numbers in front of your x, y's, and z's, but then also you subtracted by like a certain point in three-dimensional space. Okay, and that's what we get here. You can rearrange this, and you can see why exactly this point is. This is the equation for the tangent plane, and this is an equation for the plane as you'd normally expect it to be. Now, there's some other names for this. This is sometimes called the linear or affine approximation. Okay, affine is technically the more correct term, but I feel like it's used less commonly. Linear makes sense because it's basically a first order approximation of your function near this point. Basically, differentiable functions, which we haven't defined yet, it'll be at the bottom of this page, are basically functions where if you pick a point and you look nearby that point, it looks basically like a plane. Okay, and so you can say that the reason we call this an approximation, linear approximation, is that z is approximately f of xy near x naught comma y naught, and the further away xy gets from x naught y naught, the worse of approximation this gets. Okay. Now, all of that's assuming you have differentiable functions. So, in fact, the way we say something is differentiable is if the linear approximation is a good approximation. Okay, and I won't really say much about that, but in this definition on page 109, they say a little bit more. They talk about it in terms of limits and how these two things are related. But I think the most on this page, there's a lot going on. The most important thing is probably this formula here for the tangent plane, and just understanding that the tangent plane is cool because it's like, oh, geometrically that's cool, but it's also approximating your function near that point. Okay. Oh, it looks like I've gone over time here. So we'll wrap up with this slide for sure. And then I'll start with this slide tomorrow, leave it on here and explain it just a little bit more. And we'll call it a day.